Hey, welcome back to Calculus. In this second video for section 3.1, we're going to wrap up the section by taking a look at the derivative of the natural exponential function e to the x. So there's just one objective in here. We want to be able to differentiate that natural exponential function. I think I want to start off by just kind of reminding you about some of the important properties of this function. So let me scroll down here for a second. I've got a slide already. So maybe you remember that this number e, it's a transcendental number. It doesn't have a finite decimal approximation. It's a number kind of like pi, but its decimal approximation written there to, well, 5 places anyway is about 2.71828. Or I usually just try to keep in mind that e is about 2.7. It's a little less than 3. And we call it the natural exponential function when we think of it as a base of an exponential function. Comes up in all kinds of applications in biological problems, physics problems. In this lecture, we'll kind of explain what's kind of natural about it. But it's so if we're thinking about it as an exponential function, f of x is equal to e to the x, then like all exponential functions with positive bases, its domain is the set of all real numbers. So you can evaluate e to the x for any real number x. The output of an exponential function is never negative or zero, so its range is just the positive real numbers, 0 to infinity. You can see those characteristics over here in this graph. Yeah, the exponential function has a y coordinate for every x coordinate on the real line. That's what I'm saying about this domain. Every x coordinate on the real line has a y coordinate. But notice that the only y coordinates on the graph are the numbers that are 0 or more. There's no points on that graph below the x-axis or on the x-axis. So e to the x is never 0. A rule of exponents, anything raised to the 0 is 1. So the exponential function's y-intercept is 0, 1. All right. And then, well, it has some asymptotes. If you look at this graph, as x goes to minus infinity, the y coordinates never get to 0, but they get arbitrarily close to it. So in our limit language, I'm saying that the limit as x goes to minus infinity of e to the x is 0. And then on the flip side, as you let x go to positive infinity, as x gets bigger and bigger, the y coordinates on this graph just grow without bound. In fact, they grow quite quickly. We already talked about it. They grow quicker than any polynomial function, so it has no asymptote on the right. The limit as x goes to infinity of e to the x is equal to infinity. Okay, so there's just sort of a real quick recap of some properties of the exponential functions, important things about it. And then looking at this graph, I don't see any discontinuities. I don't see any cusps. I don't see any vertical tangent lines. So it appears that the exponential function is differentiable for all values of x. And our purpose here in this video lecture is to try to discover, like, well, what is its derivative? How do we differentiate the exponential function? I can't use the power rule, yeah, because in the power rule, when you're looking at the derivative of something, the variable has to be the base. Yeah, so when you're using the power rule, like a power function, the base is the variable, the exponent is not changing. This exponential function exactly flips that around. The base is constant, but the exponent is our variable. So the power rule doesn't apply. So we need to go back to first principles. So I'm going to slide down. I kind of got the calculation ready so that the video can be a little shorter, but I'll just kind of walk you through this calculation. So we're going back to first principles. I want to compute the derivative, take d by dx of the exponential function e to the x. All right, so by the definition of derivative, we're going to take a look at the limit as h goes to 0 of the function's value at x plus h. So the inputs of this thing are in the exponents, so that's where I put my x plus h. And then I subtract off the function's value at x and divide by h. All right, so that's the limit definition. And now I'm using a property of exponents, yeah? If you take e to a sum, you can write that as e to the x times e to the h, right? That's a rule of exponents. When you multiply two exponents with the same base, you add them. You add the exponents. So e to the x times e to the h is e to the x plus h. And now having done that, we can factor, yeah? I've got an e to the x term in this summoned and in that summoned, so I'm going to pull it out. So I have e to the x times the quantity e to the h minus 1. And since I'm taking this limit with respect to 0, and this factor, e to the x, doesn't depend on h, it's a constant with respect to h. So we have a limit property that says that that constant can be taken out front. The e to the x can be pulled in front of the limit. All right, so we're not done with the calculation, but what we've learned here is that the derivative of the exponential function is its value times some number. You might even recognize that number. It's the limit definition of the exponential function's derivative at 0, but I'm going to kind of bring that up at a later time. But what we got to focus now on is like, well, what is this number? What is this limit? The limit as h goes to 0 of e to the h minus 1. We're not over h. We're not going to be able to calculate the limit by limit properties canceling something because there's no way to factor out the h, right? We have to cancel this h if we were going to directly substitute it, but there's no way to factor h out of e to the h minus 1. So what do we do when we're confronted with a limit and the algebraic techniques that we don't know aren't working? Well, we look at a graph or we look at a table. So that's what I'm going to do. I'm going to scroll down here in a second, but we're going to look at a table of values to try to analyze this limit. So what are you expecting to see in the table? You're expecting me to list values of h that are getting closer and closer to 0. I should do it from the negative side and the positive side. And then looking at the output values of this expression, e to the h minus 1 over h, and seeing if we can see a pattern. All right, so let me scroll down. I've got it ready to go. Here's our table. I've labeled my column headings. On the left here, I've got the values of h, and on the right, I've got e to the h minus 1 over h. And the way I organize this table, I kind of want to read it with you top to bottom first. So starting off at h equals 1, in these cells, you can see I'm letting h get closer and closer to 0. It's a half, it's a quarter, it's a tenth, and so on. And as we do that, you can kind of see, well, it looks like e to the h is approaching something. Yeah, this value is getting closer and closer to some number. Down here, read the table from the bottom to the top. These are values of h that are getting closer to 0, but they're all negative. So I just took the negative of the values above, -1, -0.5, and you can see these output values are also approaching something, and they're approaching that same thing. So what I'm looking at in this table when I'm trying to make this guess is these two numbers. Yeah, and if I wasn't convinced, I could take numbers closer to 0 on both sides. But what are those yellow highlighted numbers close to? That's going to be our educated guess for this limit. You've already filled it in. It's 1. It looks like e to the h minus 1 over h is approaching 1 as h goes to 0. Okay, so back to our derivative computation, we said the derivative of e to the x was e to the x times this limit, so that's e to the x times 1, so that's just e to the x. So the natural exponential function is its own derivative. It's interesting. Let me scroll down where I've got it summarized with some clippings out of your text. I want to take two things here. You know, if you're ever wondering like what the definition of the number e is, it can be proved independently that this limit e to the h minus h, this is a little bit circular, but if you're taking, say, an exponential base b, then you can prove that the limit of b to the h minus 1 over h exists. And then we can just say, well, by e, we mean the number b that makes that limit equal to 1. So this computation, if you like, above, you can almost take it as a definition of the number e. But that's kind of an aside here. What we want to focus on is the second box here, that the derivative of this natural exponential function, remember the word natural just means that our base is e, is itself. So the derivative of e to the x is e to the x is what this formula says if you pronounce it. The derivative of e to the x is e to the x. Or writing it out in our language of rates of change, and this is very important, that the rate of change of the natural exponential function is its output value. So here, I won't get into this too much. We'll talk about it a little bit later in the course, but this is kind of why e to the x arises in this quote unquote natural way in science problems, because the rate at which, maybe you've seen e to the x like in, say, a biology class when you're talking about growth, maybe bacterial growth or something like that, doubling time problems. Or maybe you've seen it in a physics class where you're talking about radioactive decay and half-life problems and so on. The reason the exponential e to the x arises in those situations is precisely this statement that I've written at the bottom there, because the rate at which it's changing is its value. And in nature, that's kind of a natural growth rate. Like if you think about a bacteria population growing, it's growing under a simple assumption that the cells are just dividing. Well, that the rate that population is going to change then is going to be kind of proportional to how many there are, right? The more cells there are, the faster they're going to grow because they're doubling, and so on. So this is sort of the reason why the exponential function e to the x is so prominent in mathematics and science and applications is because of this fact that the rate at which it's changing is its size. All right, we'll talk more about that now, but or later. But let's just end this lecture with a couple of computations illustrating our new fact, and we can circle back through and practice some of our old skills. Okay, so I've got a couple of examples here ready for us to go, and I'll write these guys as we go. So the first example is just sort of some drill, practice our skills. I've got a function f of x, e to the x plus x squared plus 3. I want to compute its first and second derivatives. All right. So what's this function comprised of? It's comprised of 3 terms: an exponential term, a polynomial term, a power term, and then a constant. So when we compute the first derivative, we're going to differentiate those things term by term. So if we roll this together, we start the computation. F of x is, well, the first thing I'm looking at is the derivative of this term, e to the x. The derivative of that term is itself. And the next thing I'm going to do is, well, I have to add, and now I'm looking at the derivative of the second term, x squared. That's a power function. The power rule says its derivative is 2 to the x. And then finally, I'm looking at the derivative of the last term. This is term by term differentiation. That last term is a constant. Its derivative is 0. So if you want to kind of clean that up a little bit, there's an expression for the first derivative, e to the x plus 2x. All right, the second derivative, same idea. It's just that now when I'm doing my differentiation rules, I'm looking here. I'm looking at the first derivative because the second derivative is the derivative of it. Yeah, and once again, I'm going to differentiate term by term. I'll differentiate e to the x and the 2x separately. The derivative of e to the x is itself. Derivative of 2x, well, by the constant multiple rule, it's 2 times the derivative of x, and the derivative of x is 1 by the power rule. So our second derivative ends up being e to the x plus 2. Okay, so there's just some drill computation showing off our new skill that we can differentiate the exponential function. So for the last example in this video, I want to look at a question like this, kind of rolling some ideas together. So what's the example asking us to do? It's asking us to find a point on the graph of e to the x. So we're going to be looking for a certain value, an x value, or a point, x comma e to the x, where the tangent line is parallel to this line, g to the x equals 3x. All right, so there's some kind of good vocabulary here. Tangent line, parallel. Remember, 2 lines are parallel if they have the same slope. Parallel lines have equal slope. Yeah, the slope of the tangent line is the derivative. So I'm just kind of translating this problem. This question is asking us to find a point, find an x value, such that the derivative, the tangent slope at e to the x, that's the f prime of x, is equal to the slope of gx, that's g prime of x. So I'm just translating the question. Find a value of x for which those 2 derivatives are equal. Okay, well, looking up here at the formula for f of x, it's e to the x, so that's f prime of x is just e to the x. And we can differentiate g of x with our power rule. G of x is a polynomial, 3 times x, so its derivative is 3 times the derivative of x, or just 3. So basically, this question is asking us to find a value of x for which e to the x is equal to 3. All right. So how do we solve an equation like that? That's an exponential function. One of the reasons I wanted to do this example is to kind of remind you of how to solve that. I want to solve this equation. The variable that I'm trying to solve for is in the exponent. So you do that by taking logarithms. When you're trying to solve an exponential equation, you take logarithms and you use the logarithm that's the same base as your exponent. So I'm going to take the natural log in this case. Remember, the notation for that is ln of both sides. And the reason I'm doing that is because by definition, on the left-hand side, the natural log of e to the x is x. Natural log and e to the x are inverses of each other. And on the right-hand side, I get a number, the natural log of 3. Right? And you can get out a calculator if you want to estimate that number. It's just a little bit more than 1. I'm going to leave it an exact value like natural log of 3. So here's my answer to our question. I want to answer the question explicitly. So the question was asking me to find the point on the graph of this function f of x e to the x, where the tangent line was parallel to 3x. So I don't want to answer just with x equals log 3, because that's not a point on the graph. That's just the x-coordinate of the point on the graph. So to find the y-coordinate, we have to finish off by saying, well, let's take f of log 3. F of x is e to the x. So when I put log 3 into e to the x, e to the log 3, again, because they're inverses of each other, it's 3. All right? So the point that we seek, the point is the point natural log of 3 is its x-coordinate. Its y-coordinate is 3. So that's the point on that graph in which those things are parallel. All right? I've got a little Desmos graph ready for you. I almost kind of wish I would have switched over to it before we answered this question, but let's switch over and just kind of take a look. We'll end this video with a geometric look at what we were just talking about. So now you can see my Desmos window. I've got the function e to the x graphed in this Desmos window. I'm looking at it just for x between 0 and a little bit more than 2. So that's that just familiar shape of an exponential function. And let me throw g of x in the picture here. I drew it dotted just to kind of make it more distinguishable, but that's our function g. So it's a line, it has y-intercept 0 and slope 3, right? G of x equals 3 to the x. And then let me turn on tangent lines that I can move here. So if I turn this thing on, you're going to see a red line, and it's tangent to e to the x, and I can change the point of tangency. So what I'm doing is I'm changing where this line is tangent. And so what this question was asking us is, what is the x value that we need so that that red line is parallel to the green line? So it looks to me like it's going to happen somewhere. I'm just doing this by eye here, but it's pretty close to about right there. Yeah. So on the slider over here right now, A is about 1.9. And you can check out, maybe we can get a calculator. I'll just switch over to a Google pane here, and we'll ask Google what the natural log of 3 is. But you can see geometrically that those lines are in fact going to be parallel for one value of x, and it's very close to 1.1. Yeah, if I make x bigger than that, the red line and the green line are going to cross again. If I make x less than that value, they're going to cross again. So they look like they're parallel somewhere in this neighborhood of about 1.1. All right, let me try it. I've never tried this. If I just switch over to a Google screen here and type ln of 3, what's Google going to tell me? Ln of 3, there it is. How handy. Thank you very much, Google. The natural log of 3 is about 1.09, blah, blah, blah. So that's what we were seeing in this picture. 1.09 is pretty close to 1.1. All right. So just to recap, what did we do in this video? We learned that the derivative of the exponential function e to the x is itself. It's an interesting fact, and it's kind of a nice fact because it's not so hard to remember. Let me just bring us back to the whiteboard here. We can look at that fact one more time together, and then we're going to call this video an end. So our main punchline right there. Oh, you still can't see it. Sorry, this is kind of fizzling here. The derivative of the exponential function is itself. Super important fact. Derivative of e to the x is e to the x. Okay, thanks for listening.